Brian and Yvonne, are you ready? Okay, welcome to the Whirlwind Introduction to Computer Graphics class. My name is Mike Bailey. I'm a professor at Oregon State University and have been involved in graphics and SIGGRAPH for, well, let's just say a while now. There's how to reach me. And at the bottom of the screen, several screens, including the one at the end, you'll see a web link. The notes for this course are out there. You can get them through the ACM Digital Library as well. But if you want to go right to them, they're there, along with a bunch of other things. Some animation videos, some Blender input files, some links to other note sets. So anyway, that's a good link to take a phone picture of. Okay, here we go. So why are we here? We're here because, well, SIGGRAPH is full of a lot of things. There are so many things going on, and it's every aspect of computer graphics, and there's a lot of jargon, and the people around you are suddenly gasping with delight, and you don't know why. And so really that's why this course was created, was to make the whole week much more enjoyable if you're new to SIGGRAPH. This is the schedule we're on, and when I say Whirlwind, I really truly mean Whirlwind. We'll talk about modeling, animation, and rendering. Those are really the three big topics in computer graphics to better understand the week. We'll talk about finding more information, and I will stick around after the class is over, and if something else is in this room, I'll go outside, but I'll stick around as long as anybody would like to talk. So yeah, that's a given. All right, the graphics process. Unfortunately, we have to sort of deal with talking about computer graphics in pieces. There's this piece, and then there's that piece, and there's that piece. But really, the pieces all have to go together. And so we talk about modeling, and we talk about rendering, and we talk about animation. Let me get my pointer set up. All right, so we're going to talk about modeling, we're going to talk about rendering, we're going to talk about animation, and there's all these pieces, there's a lot of aspects of each piece, and that's why this is Whirlwind, because we want to talk about those aspects so that when you see them during the week, you'll come back to this diagram and think, oh yeah, that's how this fits in with the whole process. All right, but let's start with modeling. Modeling is the act of taking geometry of some sort and creating it in such a way that you can use it in your computer graphics. So when you do modeling, when you create geometry, really you don't start by just jumping in. You start by asking yourself some questions, because there are sometimes hard ways to do it and sometimes easy ways to do it, depending on why you're doing it. And so what's the purpose of creating this computer graphics geometry? Is it to just simply look at the appearance of something? In that case, you can be a little bit sloppier, but are you going to be using it in some kind of mathematical analysis? Are you going to be using it for 3D printing? There's a whole bunch of questions you should ask. And one of the things you should know about modeling is if you're trying to create something, you oftentimes can simplify it. And facial animation is one of those things, and I find this really interesting, is we as humans tend to look at a lot of things and think they look like faces. And so, here's some examples. A wall socket is certainly a great example. That looks like a face. You could do a very nice animation of that with some fairly simple geometry. I think this looks like Mr. Bill the puppet. Oh no. This is the stapler on my desk in my office. I think that looks like Carl from the Pixar movie Up, because of a rectangular face. These are markings on a speed bump as I drive into my neighborhood. I think that looks like Captain Crunch. And I apologize now, because once you have that in your mind, you can't unsee it. So every night when I drive home, oh, good evening, Captain. All right, well, let's look at some ways of modeling. And the one I think is kind of coolest and most intriguing, especially for beginners, is something called an L system. And here's how it works. You start with an equation. And in that equation, F means take a step forward, plus means turn slightly to your right, minus means turn slightly to your left. The square brackets mean remember where I am and then go back to there. And so with this equation, we move forward 2 steps, we turn to the right, we move forward, and then we go back to the fork, and then we go up the left. And okay, that's a way to design a fork, but why do we want to do that? But then the trick is, I take every F in this equation, and I replace that F with the whole equation again. Okay, and when I do that, I get this. So I go from this to that, to that, to that, to that. And so really by repeatedly applying the same things, I can get to a fairly good looking bush. Now this is a very famous example, a well-known example in an L system. I also added some things to this so that I could rotate it out of the 2D plane. And so, yeah, now we've got a 3D bush. And if you look closely, you can see the individual forks. You can see the patterns. But you really have to look very closely to see that, especially when it becomes very dense like this. And so this is an interesting way to model geometry. And this is an example of why you would do it really strictly for appearance. There's just not a lot we're going to do with this mathematically other than look at it, rotate it, use it in a scene. Another way that people like to model is with something called curves. And there are many different kinds of mathematical curves in computer graphics. This is one called a Bézier curve, named after Pierre Bézier, who developed this when he worked at Renault Auto Company. And here's the idea. I start with these 4 points, and I put them into this equation, and I vary t from 0 to 1. And by varying t from 0 to 1, and if I just draw to those points, I have this smooth curve. And the way the points work is the curve starts at point 0, it ends at point 3, and points 1 and 2 influence where the curve goes. I like to think of them as gravity bodies, that kind of suck the curve up towards them. But here's the great thing, is you can do things like this, and so with really just clusters of 4 points, you can create scenes. But the really great thing is if I move those points and redraw the curve, I can edit my curves. And so if I take this control point and move it up here, and this one and move it up here, and then redraw the curves, I get a smirk instead of a smile. And the great thing about this is that that equation is simple enough that this can be done in interactive time. As you pull the points around, the curve can be regenerating in real time, and so you end up, you can use this for art or for just other mathematical expressions. And it gets even better because you can extend that into a surface. And the surface, the Bézier surface, has 16 points, 4 at each corner. The surface goes through the corner points, but those other 12 are the gravity bodies. And so by pushing and pulling on the other 12, you can change the shape. And this is really what Bézier was after. He was trying to find ways of sculpting automobile bodies. But this is used in things like ship hulls and so on. It's anything that's kind of smooth like that. And once you've got that, well, you've got the numbers, you can do other interesting things with it, like contour lines, like curvature analysis. That is, you can really find out what's going on in that surface as you're pushing and pulling on the points. So again, this gets into the idea of why are you modeling geometry, and how do you pick what way to do it in order to enhance what it is you're really trying to do? If you're trying to do some math on the surface, this is a great way to go. But far and away, probably the most common geometry modeling in computer graphics is the mesh. Meshes can consist of really any kind of polygon, quadrilaterals, but typically it's triangles. And sometimes the triangles are arranged in nice rows and columns, and that's called a regular mesh. Yeah, normally you're not that lucky. And if it's not arranged that way, it's called an irregular mesh. And this comes up so much in computer graphics that there's kind of a name for it. It's typically called a TIN, a triangular irregular network, or just mesh. And when you build this into a program, like how do you do that? Well, to build it into a program, basically you create a series of tables. So here is a table of just vertices. And those vertices are the vertices on a cube. So a cube has 6 square faces. That means it has 12 triangles. There's 8 vertices, 8 points on the cube. So we'll put them all in one table. But then we create another table that tells us how to connect them. So vertex 0, 2, and 3. 0, 2, 3, all get connected, and that's one triangle. So this is typically one of the ways that you get mesh data is in a series of tables. And you can put other properties into the tables as well, like colors, like surface normals, like texture coordinates, all kinds of things. But basically, a mesh is defined by a group of tables. And these triangular meshes have become really important lately because 3D printing requires them. Okay, 3D printing, the format of geometry that every 3D printer accepts is a TIN, a triangular irregular network. And so here is one thing that I had modeled. And if you zoom in on it, yes, you can see that it is indeed a mesh of triangles. And 3D printing is just amazingly cool these days. The desktop 3D printers have become so inexpensive, especially compared to where they were like 7, 8, 10 years ago. And the things you can do with them, like I got my son a desktop 3D printer for Christmas, and he's gone absolutely crazy. You can make these snakes that they come already assembled, but they're loose. He did this fractal pyramid. It's been great fun. For my part, I took the SIGGRAPH logo, turned it into a mesh, put it on a 3D printer, and made this and used it as a cookie cutter. So yes, if you're a SIGGRAPH goer, the ability to use computer graphics to make junk food is certainly one of the real reasons we're all here. But meshes have something, a lot of things bigger for them. Yes, you can look at them, but the mesh geometry is mathematically able to be smoothed. And fortunately, these days, none of us have to know the math behind smoothing. We go into programs like Blender or Maya, and we say, smooth that sucker. And it goes from this to that, or let's do it again, and goes from this to that. And so having a mesh, even one that you've defined fairly coarsely, is not a bad thing because you can enhance it. And you can enhance it almost as arbitrarily much as you want. You can also sculpt the meshes. You can go grab a vertex and pull on it. And so here's a sphere, and if I grab that vertex and I pull on it, well, I get that. And that's not normally what we all want to do, unless you're trying to put horns on a sphere. But typically what you can do is do something called proportional editing, where while you're grabbing this point, it lets you put up a circle, and you're also grabbing all the other points inside that circle. And so now when you pull on one point, the others come with it, but not as much. And so it's sort of like you're dragging them out. And so you get much more of a smooth editing, which typically is what we wanted. You can also do things like sculpting. Modeling programs will let you do things like, well, take the sphere and let's pretend we wet our thumb and we go over the clay. And so this is all happening mathematically, of course, but we can do things like that. And by looking at it, by looking at the vertices, you can see what it's done is it's added more detail in here to make that whole sculpting smoother. And the clay analogy only goes so far because you can also add material. So imagine you had a lump of clay and you did this with your thumb and it grew out. Okay, can't do that with clay, but you can do that with computer graphics. And once you have the mesh, you can do analyses on it. So here is a mesh of a wine glass. It was created for the appearance, but you can also run analyses on it that cause it to break in physically plausible ways. I like that. Here comes another way of modeling in computer graphics. Now, you all probably had Venn diagrams in high school, right? Oh no, trigger warning, high school. But they worked like this, it was set theory. But you had two circles, and if you did a union, it left you with just the outer shell. Okay, it was combining everything that was common to, or that was in at least one of them. If you did an intersection, it was this piece where they overlapped. And you probably didn't do difference in high school, but if you had, it would be like one is taking a bite out of the other. So if this is A and that's B, A minus B would give you this, okay? And so, yeah, that's the high school Venn diagram. We use it for modeling. And so imagine I did it in 3D. So here I've got a block and a cylinder. If I do the union, it almost looks the same, but it's not. And the reason it's not the same is if I just overlap these two shapes, there is some place in space inside them both where both materials exist. And in our world, our universe, 3D things cannot pass through each other, okay? Be cool if they could, but I hit the table, my hand doesn't go through it. The reason you care about that is this overlapped is not 3D printable. 3D printers know about that 3D things can't overlap as well. And so if you sent that to the 3D printer, it would mess up somehow. Okay, different printers will mess up in different ways, but guaranteed it will mess up. But if you do the union, remember back here, the union gave us the outer shell. The union of two 3D things gives us the outer shell with no overlap in the middle. So that would be 3D printable, okay, which is important depending on why you're modeling the geometry. Intersection of those two would look like this. Difference would look like this. It's a nice, convenient way to put a hole through something. Okay, so yeah, this is important. And if you do anything with this, union, difference, intersection, any of those are 3D printable because no matter what, they've eliminated regions in common in the middle. Okay? And throughout the notes, if you're interested in trying this, I'll put in little links in here, and they're also repeated on the Whirlwind website as well. But these are free programs. Blender and Tinkercad are free programs that let you do this, and those notes will show you how. All right, let's talk about animation. I promised you Whirlwind. Okay, in the global scheme of let's put it all together, animation fits over here. And animation is just a way of getting things to move. But like modeling, you start out with, why am I doing this? What is it I'm trying to accomplish? Do I just simply want to make something move from here to here? Do I have a series of locations and I want to fit a nice smooth curve through it? Do I want it to follow the laws of physics? Do I want it to bonk up against something while it's moving? So a lot of these things, depend on why you're doing it, what amount of realism do you want, and what kind of compute time are you willing to put into it? Okay, probably the one to begin with is keyframe animation. And really, this goes back to almost 100 years, like 90 years ago, Walt Disney. And the way hand-drawn animation worked at the time, probably still does, is the senior animators got to do the cool stuff. At time 0, Mickey Mouse is here. And at time 1 minute, Mickey's over there, and so on. And that's what they got to do, and that really defined the movie. And so then they would hand that to the next tier of animators, the almost senior animators, and they would fill in some of the in-between frames. Okay, I'm gonna make Mickey look sad and like he's moping. But then they would finally pass it down to the newest animators, and they would fill in every single frame. And there was no creativity there, really, because everything had already been defined. And so the senior animators got to do the key frames. The junior and lesser animators did the in-betweens. And when computer graphics started doing this, they kept the terminology. It's called keyframe animation. Okay? Now, it's changed because if you use a program like, say, Blender or Maya, you are the senior animator. You are defining the key positions. And who is filling in the in-betweens? Well, that's the computer. And so this is great. And really, when you think about it, it doesn't just have to be motion. You can keyframe anything. At frame 0, I want the color to be red. At frame 20, I want the color to be blue. And then you interpolate color. Or you interpolate a scale factor. Or you interpolate a rotation angle. Okay, but the point is, you get to do it. And again, animation programs like Blender or Maya give you a lot of tools to do it. And typically, it ends up looking, something like this, where you've got a keyframe here, and here, 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 and here, and it attempts to fit a smooth curve, although you can then sculpt the slopes of the curves so that you get sharper motion if you want it. Okay, and again, in these programs, anything can be animated, any quantity. It's really not just movement animation. And if you're trying to make, say, a body move, well, if I'm trying to make a human move, that's a lot of vertices, that's a lot of points, and I really don't want to animate each vertex. And so what they do with something like that is they use rigging. And you're likely to hear the word rigging all week this week. But what rigging means is you take, well, they call these bones or armatures, and you hook them together. Bones is very apt. Imagine a human skeleton. You've got all these bones hooked together, but then what you do is you assign a certain set of vertices to each bone. And then you animate the bones, and the software inside the animation program brings the vertices along for the ride. I've been trying to create a little animated macaroni and cheese. His name is Mac. But this is an early test of that. But you will hear the word rigging like all week long because so much is done this way. There's also something in graphics animation called forward kinematics. And in forward kinematics, you have things that are linked together. Okay? The wrist is connected to the forearm, is connected to the upper arm, is connected to the shoulder. That's the perfect example. And all kids understand this. Okay? All kids get out their Tinker toys and they put them together like this so that they work that way. And if I rotate this one, the other two go with it because they're connected. If I rotate just this one, none of the other two go with it because, well, they're connected, but they're connected downstream instead of upstream. Okay, and then there's math that does that. And that's important for things like, well, skeletal movement, robotics. But if there's a forward kinematics, there ought to be an inverse kinematics, and there is. And it really solves the other problem. Forward kinematics is trying to solve, if I know the angles, where do the pieces go? Inverse kinematics tries to solve the problem, if I know where I want the piece to go, what should the angles be? Okay, and this is a big deal. If you want to animate somebody walking, if you just do the angles, there's a good chance their foot's not going to be on the floor when you get all done. Whereas inverse kinematics would say, put the foot on the floor, and now figure out what angles I need in order to make that actually happen. Okay? Now, the interesting thing I find about inverse kinematics is nobody ever calls it that. If you hear of it this week, it will be called IK. When people do forward kinematics, they don't call it FK. But anytime there's inverse kinematics, nobody talks the words out. It's always IK. So this week, don't use the phrase inverse kinematics. It will flag you. You don't want to do that. And why it's this way, I don't know, but it always has been. The other thing that is interesting about inverse kinematics is there are some places you could ask for this tip to be where there is no combination of angles that'll put it there. And you all know this. You know, there's that spot in the middle of your back you can't reach to scratch. So you do something weird like butt up against a door frame and wiggle. Yeah, that's an inverse kinematics problem. So while forward kinematics, any set of angles will give you an appearance, inverse kinematics, there are certain positions where you can't get the angles. There is no solution. So I find that kind of interesting too. Another animation technique you'll see this week is particle systems. And particle systems, well, it's exactly what it sounds like. I'm going to take some particles and move them around. And lots of things can be done this way. Okay, water flow, dust, smoke, fireworks. And once you know of this, you can't stop seeing it because it's in all your games, it's in all the movies, and I have no doubt you'll see it this week, even if it's not labeled, this is a particle system. And the fun part of playing with particle systems is it's fairly easy to put together in a program. Even what program you write yourself is really what you want to do is you emit the particles, you display the particles, and then you update them. Update them with gravity pulling them down, say, or wind blowing them to the side, or some sort of goal you have about how they move. And then you just stay in this tight loop over and over while your thing animates. And again, you will see this a lot this week. One of my former grad students was interested in water coming out of a hose, so he did a lot of playing with water particle systems. Programs like Blender and Maya give you a lot of tools to do your own particle systems, and really it's a lot of fun. I warn my students, unless you're doing it for an assignment, don't get into particle systems because you will never let it go. 10 years from now, you will still be enhancing that particle system. That's how cool and addictive they are. Other ways of animating, physics. Okay, physics has certain equations. F equals ma if you remember high school physics. Okay, and so if I'm going to, well, here's one I did in Blender. If I'm going to knock over all these dominoes and then have it hit the sphere and push it off the table, that's going to be tough to keyframe and have it look correct. Okay, it's real easy to do things in keyframe animation that when you look at it, you say, no, that's not how they would have moved. But if you simply get rid of keyframing and say, I'm just going to turn on the physics, well, now you do get something that looks like very plausible motion. Now, the problem is you have to give it all the physics information. Mass, center of mass, moment of inertia, coefficient of friction, coefficient of restitution, all that stuff. But if you're willing to do that, then you can do things like this. And, oh, that's falling a little too fast, I'll increase its mass. And so you'll hear about that this week. Or you'll see animations in the papers or the electronic theater where you go, yes, that really feels like realistic movement to me. And that's your cue that it probably was animated with physics. The program called, well, the big programs like Blender and Maya will do this for you. There's a program called Tinkercad, which is a web-based program, does the Boolean modeling, the Venn diagram modeling, but they've also just added a physics component to it. So we use this in a bunch of our outreach programs with high schoolers. But one thing I've discovered is 3D modeling becomes much more exciting to high schoolers when you can crash things into each other. There's something about the mindset that does that. So again, notes here if you're interested. And of course, so many movies now do water animation. Moana is probably my very favorite example of that. But water has a certain physics set of equations as well. And so keyframing droplets of water, I hate to say anything's impossible, but I think it's impossible. And then have it look good. But having blobs of water follow the equations of physics fluid flow, okay, if a program's willing to do that for you, then I'm perfectly willing to let it. Other things that come up in animation, a lot of things can be modeled as a spring. So, you know, springs are these really cool, they seem like boring things, but they're sort of self-correcting in a way. If I pull down on the spring, it exerts a force to try and bring it back up. If I push on the spring, it exerts a force to try and push it back down. And if you assemble a bunch of springs together, you can model, well, things like strings, chains. You can get them to wrap around things. And if you take that from a one-dimensional collection into a two-dimensional collection, then you can model cloth. And so in cloth modeling, typically you have, well, these pieces, but then there's springs that connect them all. And you adjust the spring parameters based on the cloth. Silk behaves differently from denim, say. Now, one of the cool things about modeling cloth is, of course, if you're applying physics, it behaves like cloth. And so if you bring up your cloth model and you give it a little shake, the physics just naturally forms these pleats. Okay, you don't ever have to go in and model the pleats. You don't have to pull vertices in and out to make it look like the cloth has pleats. That falls out of the physics, which I think is just great. Making it look like it's fallen on top of something, that falls out of the physics as well. And so you can do a lot of things, even as a beginner, by using some of these programs to do cloth animation. And if you drop it, say drop it on top of a cube or a table, then it forms, well, the pleats on the sides and this little sort of shape at the corners. And again, you don't have to do that. You don't have to sculpt points to make that look right. That falls out of the physics, which is just great. There's hybrid techniques that I'm really fond of. I was trying to animate this. Now, this is students celebrating after a football game by rushing the field. Now, what if you were trying to animate that? Okay, I know where they're all going. I know where they're coming from. They're coming from the bleachers over here, and they're all trying to get to the middle of the field. Okay, but they can't pass through each other. And so if I just say keyframe them or just interpolate where they're starting from to where they're going, they're going to try and run right through each other, which is not what I want. Is there some way to do that? Well, physics isn't exactly what you wanted. Keyframing isn't exactly what you wanted. And so people have developed interesting hybrid techniques to do this sort of thing. This is one I like. I've heard it called functional animation. To my students, I call it fake physics. They like that a lot more. But here's the idea. So in this example, I've got all these dots in a circle. Those are the goal positions. And then the program randomly shows starting positions for each dot. So it's sort of the rushing the field example, is I want them all to go to their target positions on the outside of the circle, but I don't want them to hit each other. Okay, so first, how do you make them want to go to where they are supposed to go? And so in this technique, you connect where you are to where you're going with a fake spring. And so mathematically, we just put a spring right there. This is the mechanical symbol for a damper, something that removes energy from the system. It's very much like the shock absorbers in your car. If you don't do that, then it goes towards its target and then flies past it and then flies back and does exactly what something on an undamped spring would do. We don't want that. Okay, so if I put in a spring and a damper between every starting position and every ending position and turn on physics, it'll want to go there. Okay, but that solves the first part, not the second. The second part is, and don't hit each other. And so for that, I made up another fake force. And the fake force was a repulsive force. And it worked like this. It had a coefficient in the numerator, but the denominator was looking at the distance between it and every other point. And it increased the repulsive force, the pushing away force, the closer two objects, two people were together. Okay? And this was just kind of pulling some equations out of the air. But when you combine them, the, and I want to go here, with the, but I can't hit anybody, you get something that looks like this. And so, yes, indeed, this was the path. So this green one started here, went there. Right here, it decided to take a little detour. That's to avoid hitting someone. Sometimes the detours were small. Sometimes the detours were pretty big. But the fact is they did it. And they did it without any of us having to get in there and do a lot of things by hand. Yeah, certainly you change the physics parameters. Yeah, if you made the spring stiffer, then it would go there faster, but it would also do wild things along the way. But again, yeah, that's your control. The actual motion is computed for you. And so this is something that people do a lot. Okay, one last thing under animation is motion capture. This is like inverse kinematics. Nobody calls it motion capture. It's always mocap. So yes, don't ever get caught saying motion capture. It's mocap. And you'll see this on the exhibitor floor. There are several motion capture companies. They do it in different ways, but by and large, it's like this. The model, the person, wears a suit with these little plastic ping pong balls. They're really reflective. And they're reflective to light you can't see, like an infrared reflector. Okay? And so they go through a certain motion, and all around the room are cameras in the corners and along the top of the walls, looking at them and triangulating. And so there's infrared lights that are lighting these things up. And so what the cameras see is they see bright reflections. And so from that, they know that that one ping pong ball is on a line right here. But then another camera saw it on a line right there, and another camera saw it on a line right here. And so sort of like GPS, it's triangulating that position. And it can do this very fast. The systems today are very fast. And so it's really keeping up with the motion of the character. And so if you see some complicated motion in a movie or a game, if you see somebody kickboxing in a game, chances are that was mocapped. Okay, that's very hard to do in keyframing and make it look realistic. So anyway, you'll see some mocapping examples out on the exhibit floor, and that's how it's done. And then mocapping has gotten really sophisticated, is they now have units that will fit on your head, and it will mocap your face. If you wrinkle your eyebrows, it'll catch that. If you blink, it'll catch that. I can't imagine walking around acting with that thing on my head, but people do. And you'll probably see examples of that as well. And also just recently, amazingly enough, people are mocapping animals. Now, I don't know about you cat lovers. My cats would have clawed me to death if I had tried to stick little ping pong balls to their fur. My theory, and it doesn't mention it here in the YouTube, is that they sedated the cats, glued the ping pong balls to the fur, and then let them wake up and go through whatever motion. But you can imagine, when a cat, say, jumps from the floor up onto your kitchen counter, onto the food you've just prepared, there's a certain motion there. And I just can't imagine capturing that adequately in keyframe. And so this is perfect, as long as you have a cat that would put up with it. Okay, that's animation. The other thing we wanted to talk about is rendering. And rendering occupies this space. And really, the output is meant to be pixels, picture elements of a variety of colors. And so somehow we have to take geometry, and somehow we have to get that geometry moving in animation, and then somehow we take all of that and make a scene from it, a scene that we can all look at. And like the other two, you always start this with a list of questions. Why am I rendering this? Okay, what amount of realism am I trying to get? Do I really want it super realistic? Do I want reflections? Do I want refractions in it? Okay, how much compute time am I willing to put up with in order to get it? Do I want the illumination to be local or global? And we'll talk about that in a moment. Okay, do I want shadows? Shadows are cool, but they take more time to compute. So anyway, you try and answer those questions, and that sort of guides which of these techniques you use and how you end up using them. First of all, before we get too much into rendering, there are techniques called non-photorealistic rendering. Okay, this is called toon rendering. If you look at hand-drawn cartoon animation, there's not many colors. Okay, across a character's face, there's maybe one or two colors. Okay, so they decimate the number of colors, and then they also put a sharp black line in between the sections. Well, there's something appealing about that way of rendering. It looks comfortable to all of us. We've all grown up with cartoons, and so you can do that. You can do that digitally. And so here's a picture my friend Steve took of the castle in Washington, D.C., and then you apply the toon rendering to it, and you get the crisp edges. I like this for architecture. I like it because it really shows the lines on different buildings, okay? But a lot of people render this way because, well, they like the way it looks. Also, another way of non-photorealistically rendering is to simply do silhouette edges. So here is a 3D shape, and if I render just the silhouette edges, Then I get something like that. And this is really cool to animate because it's like you sort of get a ghost cow romping across the screen. It's really kind of cool to render with just the edges like that. Just the silhouette edges. Not all the edges, because that would fill the surface with a lot of triangle edges, but the silhouette edges. And it turns out in interactive work, when you're doing graphics on a workstation, then you can write shader code, and it actually is that simple. This is how you look for silhouette edges, is you do a little bit of vector work and it identifies the silhouette edges. So anyway, this is another form of the non-photorealistic rendering. Okay, lighting. Why do we care about lighting? Because if you don't do it, then all your objects look like a blob, whereas it's applying the lighting that makes them all look 3D. And so this is really important. And it's super important in games, and it's super, super important in movies. And if you watch a graphics animated movie, Pixar, Disney, DreamWorks, stay for the credits and look at how many people have the term lighting in their job description in the credits. It's a big deal, okay? Lighting in, say, graphics movies, the trick is to make it so you can see everything you're supposed to see, not see things you're not supposed to see, but not have it obvious that lighting is in there. It should just appear very natural. But this is what we want to do. And there are terms for the lighting, global and local. Local illumination means no matter how many objects I have in the scene, I'm going to take the light and shine it on each of those objects. And even if one object obscures the other, I'm still going to do it. I'm still going to let this light up that, okay? Because I can do it quickly. Whereas global illumination means there is interaction between the objects. The light lights up this, but light that comes off of this goes over there, goes over there, goes over here. It looks more realistic, but as you can imagine, it takes longer to do. Okay, but again, these are the trade-offs that people make when they want to do the lighting. So in computer graphics, probably the simplest way of doing lighting is something called ambient, diffuse, and specular. Ambient is just sort of constant light that just appears to be bouncing around everywhere. Diffuse is intensity variations around a curved surface. And specular is highlights, shiny spots, that sort of bounce off the object. And typically you can control the amount of each of these up to a point, but you put them all together and you get a scene that looks like this. And the significance of this is not that it's terribly sophisticated, but it's fast. And so this is easily done at interactive speeds, is you can have a very complicated scene, turn on the ambient, diffuse, specular lighting, move it around interactively, animate it all you want, and everything will keep up. And it looks nice. Now, for more sophisticated lighting, well, there's something called the lighting equation. And it's a messy calculus equation that I didn't want to put in the notes, but it's there. And if you Google it, you can find it. But basically, here's what global illumination is really about, is I've got this point P here, and I'm looking at it from an eye position up there. Now, the point P is gathering light from all sources around this hemisphere. So all the other things in the scene, light sources, other objects, they are bouncing light, and it's all being collected at that one point P. And that one point P then is reflecting it. Now, when things reflect light, they typically reflect it in kind of a pattern like this, but we don't care. We only care what we can see from the place we're viewing the scene. But as you can imagine, the math behind that is pretty significant. but the images you get out of it are beautiful. Okay, so again, what that messy calculus equation would have said is the light that's shining from the point P to your eye is a sum of all the incoming light that it's hitting it and how it's being reflected back out. Okay? Now, of course, every point P in your scene is undergoing this same equation. So again, it can be very time consuming, but you get things that look like this. And so in this, the left wall here is green, the right wall is red, the back wall is white. These objects are white, but you can see that the torus is getting some green reflection from the wall. Now, and you've probably done this too, is if you're wearing a bright red sweater and you go stand next to a white wall, you can see some of the red from your sweater ending up on the wall. Okay, this is what global illumination gives you. And so this looks a lot, nicer, more realistic, because it is taking into account light bouncing all through the scene. Now, how do you actually do this? Well, when light hits a certain surface, it doesn't do angle of incidence equals angle of reflection, like we all learn in physics class. Depending on the material that the light hits, it will bounce out in some sort of pattern. If it's a fairly smooth material, it might bounce out in a fairly narrow pattern like that. If it's a rough material, well, it'll bounce out like all over the place. And people have run experiments and have documented what that dispersion pattern looks like for different materials. Glass, obsidian, shiny metal, rubber, rust, things like that. And so just using that, you can take light coming in and redistribute it out into the scene. Now, that's the good news. The bad news is light comes in and a lot of arrows go out. Okay, and that you now have to deal with that. So, let's do this. So let's say we have this scene and we have a surface here and a surface there and a surface there, and here's our light. Okay, so the light is there. Oftentimes it's easier to do the tracing from your eye than from the light. You can trace from the light, but it's easier from the eye. So the eye looks over here, and it's almost like the eye is emitting light. What happens when it hits that bottom surface? Well, it bounces out according to a certain pattern. Well, you could make that pattern right by putting an infinite number of arrows there. We don't want to do that, but you could. And then we follow each of those arrows. So now we were first following this one arrow. Now we're following all the blue arrows. Some of those blue arrows will hit the red surface. Well, that generates more arrows because each one of these, when it hits the red surface, it generates that dispersion pattern. And so now some of the red arrows hit the green surface, and even more arrows come out of that. And so on and so on. And finally, we get it all done, and we see which arrows actually hit the light source. Now we can trace that backwards and say, okay, that means this surface got lit up, this surface didn't, this surface is in a shadow. And this is path tracing. And basically, we are tracing multiple paths through the object. Now, you're thinking, this has got to be a gazillion arrows, and it would be if we followed them all. But what we do instead is we do a Monte Carlo simulation, meaning we randomly, kind of controlled randomly, pick certain arrows to follow and leave other arrows, okay, we're not going to follow them. Okay, but some of the really spectacular scenes you see in computer graphics do that sort of thing. And because we're following the arrows through materials, we can handle reflections. Because if you hit a reflective surface, you bounce, it's a mirror, you bounce the ray and then see what else it hits. If you hit a transparent surface, you refract, you bend the ray and see what else in the scene it's hit, and so on. You can do things like soft shadows because some of the rays get blocked and some of the rays don't. One of the knocks on computer graphics shadows when people first started doing them is they were too good, they were too crisp. Like it was a 1 pixel difference between in shadow, not in shadow. But because we have all these dispersed rays going out, there's going to be some places where some ray brings light to that point and other rays don't. And that gives you the soft shadow effect. Yeah, more here. And in these chapter headings, you see it as well. If you look at the chapter headings closely, yes, that green background is being reflected in the pink characters. So, if you would like to experiment with this, Blender lets you get at that and lets you set all these properties and lets you set up reflections, which we have here, and refractions, which we have there, and so on. And there's a lot more techniques to rendering as well. There is something called subsurface scattering. And without going into the math, let's go into the math a little bit. So there are some surfaces, some objects, some materials like skin, wax, milk, where the ray doesn't bounce off the object. It actually goes into the object, bounces around a little while inside, and comes back out. Again, wax works this way. And so that's a technique that models that in rendering called subsurface scattering. And so this is an object without it. This is an object with it. And you can see that this does look a lot more waxy than this other, the first object. And there's a lot of other tricky lighting situations. Hair is tricky. Now, when you look at the top of someone's head, if you've ever looked at the top of someone's head outside, you don't see a kind of an ellipse of brightness, you see a halo. Well, what happens is the hairs on our head have two curvatures. The cross-section curvature is like a circle, it's very tight, but our hair also drapes down the side of our head, and that's a much looser curvature. And so we're kind of getting this more elliptical halo effect. Fur, animal fur, is also a very tricky lighting thing. Anytime you see a movie where the animal fur looks really good, things like the computer graphics Lion King is a great example. That took a lot of work, a lot of math. Feathers are interesting too. Feathers, again, have very interesting property because it's not a solid feather. It's these little strands of feather material. And so they do interesting things with bouncing the light. Okay, so that's modeling, animation, and rendering. I wanted to show some cool images, sort of like you'll see this week, and talk about what makes them cool, what makes them that way. And so this is one that Andrew Glasner did. It was an article he wrote on Celtic knots, and so it's the shape that he was really interested in. But I've used it here because there's some interesting surface modeling that cause these twists. That is, the twists look really good. You don't see a place where there's a jagged edge in the twist. It's really doing the math of the twist really nicely. But the part I really like are these divots. And so you see these divots, and the divots are there. You know the divots are there because of the lighting. is anytime you see a divot, so let's say we had a divot and the light is shining this way, well, right here, the divot is going to be very bright because the light's shining directly into it. Over here, the divot's going to be dark because the light's hitting it at kind of an oblique angle. Okay, and you can see that. So like this divot right here, part of it's bright, part of it's dark, and that's what gives us the visual clue that there's a divot there. And your divots could look like a golf ball. They could look very regular, but he's done a really nice job making these more random so that it looks like they're there. They're sort of almost by the accident of the way the material was created. So that's, I think, very cool. And you'll see things like that this week. This was actually accepted as a poster. So if you go to the poster sessions, you might see this one. This is looking at foliage rendering. And foliage rendering is a big deal because forests show up in games, forests show up in movies, and you can play all kinds of tricks to simplify the foliage. One trick is somebody goes outside, takes a picture of a forest, and then they map that image onto a flat polygon, a flat quadrilateral, and put it off in the distance so it looks like there's a forest there. Well, there isn't. It's a flat image, and as long as you don't try and go walk through it, yeah, you'll be fooled. And games do this a lot. Games do that. The sky in your games is probably a photograph of the sky mapped onto a quadrilateral. So there's a lot of that happens. But this is all 3D, and this was 3D you could walk through. And what she ended up doing was using generative AI to do some of the characteristics, is make this tree look like a maple. And that would go give the bark, that would give the leaf structure, that would give sort of how the branches are spreading out. And then she used geometry nodes in Blender to actually create this. But walking through it worked just fine, and changing seasons worked just fine as well, because the generative AI could keep track of, oh, in fall, this kind of tree produces this set of colors of leaves. So this one was kind of cool. This is atmospheric rendering, and this is really tricky. And why do you do this? Flight simulators want to do this. When they're training pilots, pilots are going to see the world in a lot of conditions. They're going to see it clear sky, they're going to see it cloudy, they're going to see it with fog, they're going to see it with haze in the air, with smoke in the air, with snow in the air. And so being able to put different atmospheric conditions in your flight simulator is a big deal. But the math is hard. Okay, if you can just kind of envision, okay, when we had rays going around solid objects, okay, that was tricky enough. But now imagine what rays do when they're in a fog bank. And of course, there's different densities of fog that could be used. And so that's what's going on here. And also the position of the sun matters a lot. You know, if you've ever watched the sunset and watch how the colors change as the sun gets lower in the sky, well, from the air, you're constantly seeing the sun in a different position. And so modeling this. So this is a really extreme example of tracing rays through a scene, but having to handle a variety of materials and dispersion patterns. All right, this one's good. Probably we're all getting hungry, it's close to lunch. But yes, this is gummy bears. And this was done, well, the interesting thing that I've heard about rendering gummy bears is they both reflect and refract. And so you can tell by the bright spot, there's a certain amount of reflection going on, and you can tell by the, well, looking through it, that there's a certain amount of refraction going on. And then, of course, the gummy bear has a color, and that acts like a color filter. So if you put a red gummy bear and a blue gummy bear behind it, you won't see the blue, because the blue that's coming towards your eye gets filtered out by the red transparent gummy bear. So that's what's kind of cool about this. And then one of the things that you're going to see a lot is real-time great scene generation. I'm not exactly sure what to call it. It's path tracing, but it's also some ray tracing. But graphics cards these days are being built with accelerators inside the GPU chip that can accelerate the processing of these rays. And really, that's the bottleneck. If you write software to make that kind of scene, the bottleneck is processing the rays. What do they hit? How do they hit it? How is the dispersion done? But that's being built into GPU hardware now. And so you will see some amazing things on the exhibit floor that you will swear, this must be part of a movie, but it's not. It's real time, interact with it. And so this scene, which you saw a moment ago, this resolution is 1920 by 1080 pixels, and it was able to draw this whole scene in under 3 seconds. And if we had simplified it or cut down the resolution, it would have done it even faster. Okay, but there is reflection going on here, there is refraction going on here, there's texturing, and this was also part of an animation. So there was movement going on here as well. You will, guaranteed you'll see this week. And then I also want to point out that these tools like Blender and Tinkercad are such that they have really lowered the barrier to entry into computer graphics. And that's great. That's great for all of us. No matter who you are, what your background is, what you're trying to do, you can usually find a way to do it without a lot of difficulty. Yes, you can set 1,000 parameters to change it, but getting it to work at all has never been this straightforward. And so this is a program called Tinkercad, and this was what one of our, we do a lot of K-12 type outreach with computer graphics. This was middle schooler and elementary school kids do this kind of thing. This is with Tinkercad, like, what? Wow, that's pretty cool. And then there's a part of Tinkercad is called code blocks, which is like a programmable part of doing the modeling. Okay, it sort of lets you add equations, but it's one of those puzzle piece drag and drop paradigms. And this is what one of the kids did too, is she wanted to make that shape, but the code to do it is about this small, because she just went up a layer at a time. She just put a loop in there that said, and go up a layer, bring everything in, do it again. So that's what we're all up against. This is who's coming right behind us. Well, sort of right behind us, because it's middle school and elementary school. At the high school level, we get things like this. Every summer we run a 1-week high school Blender camp, and this is the kind of stuff they do. And they come in knowing nothing about computer graphics, but they end up doing things like this. And again, I'm both excited and scared of when they start to hit SIGGRAPH, when they start to discover what you all have discovered now. Okay, so summary of the process. We talked about modeling, we talked about rendering, we talked about animation, and they all have to combine. Separately, they are different things, but in making a final computer graphics scene, they all have to combine together, and they all have to work together. The animation has to look right. The rendering has to appear realistic. And the modeling, it all starts with the modeling, so that's important too. So conclusions of SIGGRAPH are, this is going to be a busy week for you all. I hope you're ready for it. I hope you slept extra the last week, because so many things are going on. You're going to try and get to all of them. Some of them, like this course apparently, are being recorded, and so you'll be able to see it afterwards. Some things are not. Okay, some things are archived, some things are not. Pay a special attention to the things that are not going to be archived, because if you miss those, you've missed them forever. Okay, if you've got a choice between two things and you realize one of them is going to be archived and the other's not, probably go to the non-archived one. Okay, you can always pick up the other one later. And take what you find out this week and figure out how it relates to your goals. I know it's tempting. You come to SIGGRAPH and there's all this stuff, there's parties, there's other events, but this happens a lot. I call it SIGGRAPH buyer's remorse. You get to Friday morning and you realize all the things you didn't go see. You think, oh, geez, I missed that, I missed that, I missed that. Don't let that happen. Really, really look at what you're here for and prioritize what you go see, because a lot of it will never come again. Okay, there is a section of the notes on finding more information. It's not here, but it's on that website. This one, this one right here. And it starts looking like this. And basically, it's a list of references that I like. And they're all references that I own, or at least I've borrowed somebody else's, so I can vouch for them. There are probably very good books listed there that I simply don't know about or can't vouch for. So don't take this as the end of the story. But there's a lot of stuff in there. So if you're interested in rendering, there's a list on rendering references. If you're interested in web graphics, there's a list on web graphics and so on. There's also a list of professional organizations like ACM, like SIGGRAPH, and there's a list of upcoming conferences as well. SIGGRAPH being the best, of course, in my opinion, but there's a lot of others, depending on what you're interested in. And so that is all out there as well. Also, on that website, there is other notes. And so these are classes that I teach at the university. Each of them has a note set. You're welcome to them. You know, have at it if it would help you. Yep, this is out there too. And there's notes for some of the K-12 things that we do. So if you're interested in getting some middle schoolers interested in Tinkercad, this gives you places to get started. And finally, on the goofy side, if there was a merit badge for this class, and there isn't, but if there was, it would look like this. And I can't take credit for this. Andrew Glasner, who's teaching courses tomorrow and the next day, he came up with this idea of designing a merit badge, and he used Copilot, and he gave it some prompts about, hey, design a merit badge that looks like this, and Copilot knew what merit badges look like. And he showed me, so I asked if I could steal the idea. And so I put in stuff about the Whirlwind course, and this is what it gave me. So if by chance some year SIGGRAPH does merit badges for courses, this is what it would end up looking like. Okay, thank you all for coming. It's a thrill to have you here. Have a wonderful week, and we'll be happy to hang out here as long as any of you are hanging out here. Thank you.